Yeah, okay, welcome back. Yeah, today we are going to learn about some numerical integration. So that among the several types of the numerical integration, yeah, today I'm going to show you the Gaussian quadrature. Yeah, so let's keep going. So that today our running object is uh, running about the Gaussian quadrature. So that I think the 2 years ago in the numerical analysis classes, so I think I introduced some trapezoid method or other Simpson method. So today, that's why we should learn about the numerical integration. Let's record the local stiffness matrix, the general equation of the local stiffness matrices is looks like this. So in here, so that you should integrate this part as in the whole domain, but depending on your system, if we have one-dimensional truss, at the time we have and also we assume that cross-section area is always constant, this become the integration with respect to the unit direction. If we have some 2D dimensional element, at the time we should consider the thickness, and then we should integrate the whole surface area. Although we do not learn yet about the three-dimensional element, but at that time we should integrate the whole domain region. So actually we use a very simple shape function. For example, our shape function always linear function, so that the b1 may be always constant. So that at that time we don't need to worry about those kind of numerical integration. However, I also do not introduce more detail. However, when we use a Q4 element at that time, so shape function may be the with the linear part, and then we have a non-linear part, so the total b1 element become non-linear function. So at that time we cannot we should perform this numerical integration part. So that, however, computer cannot integrate the symbol mathematical equation, so we can only perform the numerical integration. However, MATLAB can support the symbol-based numerical integration. However, most program, for example, Fortran and C or other Python, they cannot support those kind of symbol-based integration. So at that time, we should perform the numerical integration. So among the actually, we already know that how to integrate some function. So today I briefly introduced or reviewed about the Gaussian quadrature. So yeah, let's start the Gaussian quadrature. Yeah, actually, Gaussian quadrature to integrate some function. So we have some sampling point. Yeah, in your high school, what is the integration? Integration is area below part. If the function has only positive value, so how can we integrate it at first time before you guys learn the differentiation or integration? Maybe you guys can study learn how to integration is some using those kind of stack procedure. Yeah, the area of the bar may be similarly integration function. Yeah, so this is a way to the Gaussian quadrature. Yeah, in here, yeah, 1-point sampling means that if we have some arbitrary function, yeah, I want to choose the simple function, and then maybe I have some ranges, so that when we choose the 1-point sample, yeah, so at that time we easily expected these values are same, so that's the concepts of the Gaussian quadrature, especially 1-point sampling. Yeah, so we start by considering following the integration. Yeah, so we are going to fix the ranges from -1 to the +1 value. At that time, yeah, so yeah, easiest way to the selecting midpoint. Yeah, at midpoint we have some specific function value, so at that time maybe the area, the value is twice value is nearly same the integration this function, so we can easily expect the integration value is maybe similar, very similar the function value at the midpoint, and twice. So those concepts we can generalize this formulation as look like this, and then yeah, if we have some more sampling point, yeah, in here, yeah, sample we in this time, yeah, we only choose the only single sampling point, so that the midpoint is a very good way, and then and here, yeah, so and then the twice is why we choose the twice. It is because that the interval range equal to 2, so that maybe this length is equal to 2, and this height become the y equal 0, so that become the rectangular area, so that maybe we can easily expect it the integration this function from to the -1 to 1 is equal to the 2 times the interval ranges, and then at multiplication at the center point. Yeah, if we have more point, yeah, we can say that some function value at specific point, and then with some actually interval ranges, but sometimes we call it this is a weight factor. Yeah, depending on your weight factor, we can match exact integration value. So yeah, although in here I'm introduced only single point, so that this function function area and then this rectangular area we can expect the you can expect the both area nearly same. This is a Gaussian quadrature. So and then yeah, but to increase the accuracy of the numerical integration, actually maybe 2 years ago I introduced the trapezoid method. What is the trapezoid method? We have some function in here. So what is this? Yeah, this part, yeah, this equation looks like this: fa plus fb. Yeah, what is the fa? Yeah, this length is fa, this length is fb, and then what is this? Yeah, here. Yeah, what is b? This length is b minus a. Yeah, they assume that this cross this inclined cross rectangular, this indicated that this cross-section area, so that trapezoid method is the easiest way to obtain some numerical integration. However, it will have some error. Actually, the exact curve is they have this amount of the error. Trapezoid has always limitation. If you this function, if you this function is a linear, so that always equal to same. But if you is not at that time, the trapezoid always has some large error. And then what is the Simpson method? Do you remember? The Simpson method is we introduced the one more point. So what is this? FA and F center point, and then here, so that using similarly, maybe trapezoid, same cross-section area. At that time, error may be slightly decreased. So that similarly, Gaussian quadrature has first single point is a very similar trapezoid. However, when you increase the 2-point Gaussian integration, it looks like a Simpson method. So that in the Newton, this method is a Newton-Cotes. We normally say that Newton-Cotes method. However, compared to the Newton-Cotes method, Gaussian quadrature shows a very highly accurate integration value. So let's think about here Gaussian 2-point sampling. Let's try to the 2-point sampling. Let's integration this function again. This is a general form. However, in this time we use a 2-point Gaussian formulation, so that general form can be changing the W1 and Y1 plus W2 and Y2. So and then in here we should obtain these two wave function, and then we are not yet the exact function value. We don't know that which position is a exact position. So in the previous 1 point, we assume that always x is equal to 0, center point. However, in this time we don't know yet about where is the exact position. So that means that we have 4 unknown parameter. First W1 and W2, and actually Y1 or Y2. However, you guys can know that exact position. We can easily know that Y1 and Y1 is x1, Y2 is a function value at x2. So that we have 4 unknown parameters, so that we can assume that this function can have some cubic function. In the cubic function, they also have some 4 unknown coefficient. So after the match relationship, so we can get some 4 unknown coefficient. That's just following. Let's try to perform the integration. So after adding this function in here, so maybe they can be showed then. However, this function has some function is a even function. This function is a odd function. This function even. This function odd function. So that we don't need to integrate this odd function. The only remaining thing is a C0x, and but the interval is twice, so they become the 2C0, and then this function can be the 3 over the C2x3, and then after adding this value, this becomes 2, so that finally we reach this value. That's very simple analytical integration. However, in here we assume that Gaussian method, so that the two weight are same, and then the position actually, sorry, there are some mistake. Yeah, minus sign. We need some minus sign. It is because that we only integrated from the interval ranging from -1 to the 1, so that if we select the some Gaussian point, yeah, only sample point, only single point in the center point. However, if you use a two sample point at that time, this interval may be same. So that with those kind of assumption, maybe interval ranges, yeah, a, this is minus a, so that I choose the x is a plus minus a, and with the equal weight w1 and w2, so that, yeah, this part become a, and then this, we are indicated that this part is ag. So that let's think about ag. What is the ag? Yeah, w and function value at x equal minus a, and wave function with function value at x equal a position. So this value we can easily obtain. How can we obtain? Yeah, let's back into the previous slide. So we assume that y equals c0 plus c1x plus c2x square c0x3. Yeah, here. So that after the insertion minus a and plus a, and then this would function can be cancelled out. The remaining thing is c0 and plus c2 a square with twice with the wave function. So that right hand side looks like this. And then, yeah, let's check the some error. In the previous slide, a equal to the 2c0 plus 2c2 over 3, sorry, and then minus, yeah, 2wc0 plus c2a square. Yeah, this is an error. Yeah, actually we expected these two integration value must be equal. However, due to some numerical, every time, numerical method has some error. So how should do? What should do? Yeah, next thing is we should reduce this error. Yeah, minimum error. How can we minimum this error? Yeah, only thing, yeah, what is the unknown coefficient? Yeah, c0 and c2 is an unknown value. Also w and a0, yeah, unknown coefficient. However, depending on the c0 and c2, yeah, w and a2 can be determined. So that c0, and actually, yeah, we are integrated arbitrary function. That means that c0 and c1 and c2, c3 is a arbitrary value. Yeah, any function, any shapes of the function, yeah, this error we expected have some minimum value. So that's the way. Yeah, how can you obtain the minimum value? Yeah, the easiest way, yeah, deriving this value equal to 0. Yeah, we can expect this value. With this equation, we can reach proper w and a value. After the derived error with respect to the c0, so that the remaining thing is 2 minus 2w equal to 0, that could indicate that w is equal to 1. And then the error value derived with respect to the c2 equal to 0, yeah, that become 2 over 3 minus 2a squared w. And then we already know that w is equal to 1, so that, yeah, and then cancel out. The remaining thing, a is equal to the 1 over 3 root, so that the value looks like this. That means that our real integration point x is equal to the root 3, 1 over root 3, and then minus 1 over root 3, and Gaussian weight is equal to 1. Yeah, this is a two sampling point for the Gaussian quadrature. so yeah, we don't have enough spaces, so that some integration function, arbitrary function, so that result is equal to the w is always equal to 1, and then function value at this point is always same? No, not same. Nearly error. We can expect the minimum error between the two analytical integration and numerical integration. This is a Gaussian quadrature with two sampling point. So yeah, if you add one more Gaussian point, you can use also the 3-point Gaussian quadrature, and then you can also use a 4-point Gaussian quadrature. So at that time, with a single point, point is equal to center point, and then with the two sample point is 1 over root 3 plus minus, and then 3 point is with the center point, and then maybe you guys can derive these values, and also although 4 point, you guys can easily derive a 4-point Gaussian quadrature point, so that so with a single Gaussian quadrature point, maybe the function, if the function has some linear function, numerical value also exactly same, and with the second point, with the 2 point, maybe the cubic polynomial equation shows exact same value. Similarly, in here with the 6 unknown variable, with the 6 unknown variable, maybe 5th order polynomial equation will be matched exactly in the 4 point unknown coefficient 8, so that maybe 7th order polynomial equation will be exactly matched to this result. So that this is a concept of the Gaussian sampling. But what is the limitation of the Gaussian quadrature point compared to the trapezoid and Simpson method? If you guys can choose any ranges in this function domain. However, this Gaussian quadrature formula only work between these ranges. This is a limitation of the Gaussian quadrature formulation. So, but in the next example, I'm going to show how to apply this Gaussian quadrature any integration ranges. Do you have any idea? Actually, this Gaussian quadrature only working on these ranges. However, normally our integration ranges are arbitrary ranges. So at the time, how can we use it? Can you guess it? Some guys can easily expect that we can changing the ranges, so that this is some isoparametric formulation in the FEM method. So, but I'm going to introduce more detail. So next is let's try this integration with the different ranges. Integration over the A from A to B, but instead of the from -1 to 1 needs the transformation. How can we changing? Changing variable. In your difference calculation, so you guys can easily expect it. This A become -1, this become B become 1. How can you changing? We have some different. This value is x. We should changing t. So we can expect it those kind of linear relationship from when you put some of this value b t must be become 1, and then when you put some the minus 1, a plus c0, at that time minus 1. So how can we changing this is a simple linear algebra equation. We can obtain those kind of solution. In here a and b is already known variable, c0 and c1 is only two unknown variables, so that we have two algebra equations, so that we guys can obtain this t relationship. So that, and then this is a inversion. From here, after taking the derivative, we obtain the b minus a and dt. This is a constant value, so that we can changing the dx as using the this relationship, and then x in here, x is equal to the b minus a multiplication tip and b plus a over the half. This is a same, and also b become 1, a become minus 1, so that this is a transformation of the some equation. So okay, I prepared some result. So that let's trying to this very cubic equation. So that the exact result is 4.75. So using the trapezoid method, the integration ranges, for this purple area is equal to the 5.5. However, using 2-point Gaussian quadrature, this inclined rectangular purple cross-section area is exactly same. So that let's perform this integration. How can we do this? First, we should changing the integral ranges, so that they have those kind of relationship. 2 become 1, 1 become minus 1, and here dx become the over dt has in here. It looks like this, and x equal to the t plus 3 over 2. And here, but please be sure that our integration point x is plus minus, but in this time we changing this become t, so that t is become the 1 over the root 3, so that you should adding the how can we do this? General form is w1 y1 w2 y2. This is a Gaussian quadrature. Weight always 1 in here, and y is x t equal to the 1 over root 3 and minus 1 over root 3, and then simple summation. So that how can you guys do this? After the I prepared some result. So and then please adding this value to your simulation. Maybe this is x plus 3, so that you guys can adding this value in here, so you obtain this value. The result is nearly 4.75. This is a Gaussian quadrature. So that although we have some arbitrary integration ranges, so we can changing any integration range to from -1 to 1 ranges. This is a mapping. However, let's record our general local stiffness equation in the truss element. In truss element with cross-section area, so we will maybe have those kind of relationship, but how can we integrate from 0 to 1 or from A to B, depending on the length of the element. Normally we assume that our element length is equal to L from A to B, blah blah blah. So at that time, how can we perform this integration by Gaussian quadrature. Yeah, our Gaussian quadrature, yeah, maybe we should have those kind of lengths. The length is equal to become 2, but they have a different size, so that, yeah, 2 amplified, I increase the size of the, sorry, yeah, this technique has give us some very benefit. Yeah, so in here to integrate this equation, they become not all the cross section area same, but in here maybe different ranges. I'm going to use some s variable in here, the s, x, and here s, so that they have different ranges but the same equation. Yeah, they will return the same value. Yeah, however, yeah, let's think about, although you have a different element length, however, integration performed specific ranges. Yeah, what is the benefit when we use this method? Yeah, let's think about, we have several element with different size. Sometimes the length is equal to L1, L2, and L3. Yeah, every time when we obtain some local stiffness matrices, yeah, we don't need to any numerical integration yet. It is because we use a linear shape function, so that this, inside this part always constant. Yeah, you guys can no need to worry about this integration. The result always return to the length of the element. But yeah, but when just assume that you guys use some nonlinear shape function, so that at that time you should perform some numerical integration to obtain the local stiffness matrices. However, when you using this Gaussian quadrature simulation, so at that time you guys must be changing these three different ranges become to the match. The length is equal to 2. So that all integration perform the same element size of the integration ranges, so that it will sometime it will be very helpful when we use this Gaussian quadrature formulation. Actually, variable changing equation. We call it the isoparametric formulation. Yeah, actually our Logan textbook at the chapter 10, yeah, the chapter title is isoparametric formulation. Actually, this isoparametric formulation based on the Gaussian quadrature integration. It is because we can only perform the numerical integration, especially Gaussian quadrature, in the specific domain ranges. Yeah, in the one-dimensional integration, it can be performed from -1 to 1 ranges, or if you want to perform the numerical integration in the two-dimensional spaces, you can only perform the specific domain. Yeah, you guys can easily expect it. Yeah, from -1 to the -1 to, yeah, this is a numerical integration area for the Gaussian quadrature in the 2D system. So next slide is introduction of the Gaussian quadrature in the two-dimensional spaces. Yeah, so we have some those kind of function with integration range is a specific -1 and 1 ranges. So at that time, yeah, you guys can do this. Yeah, in the previous slide, we perform the one-dimensional numerical integration using Gaussian quadrature with the general formulation can be changing the wave function with a specific function value. Yeah, and then although this inside function can be changed, however, so you guys can also perform the numerical integration once again, so that with the wave function with the function value, so that this is a general form of the two-dimensional Gaussian quadrature. So in here, so we have some specific domain, -1 to 1 from -1 to 1 domain. So in here, in the two-dimensional cases, we can perform the only single point Gaussian quadrature. This single point Gaussian quadrature will return the large error than other 4-point Gaussian quadrature. In the one-dimensional cases, we can perform the two-dimensional Gaussian quadrature formulation. However, due to the increase of the space domain, so that we should perform the nth 4-point Gaussian quadrature, so that the result can be expected looks like this. This also can be easily derived exact point. And however, in the previous slide, in this domain, the exact point looks like this, and then Gaussian weight is equal to 1, so that in the 4-point Gaussian quadrature, weight factor is equal to 1, and then position is s plus minus 1 over root 3, t plus minus 1 over root 3, I and I. So that this is a numerical integration. So let's try to do some example of the two-dimensional Gaussian quadrature. So that let's try to do this integration in here. So exact solution, you can obtain the 2 log 3. The value is 2.197. So that when you perform the 1-point rule, so that only single point and then specific point in the center point, so that this function value is equal to at point 0, so that this is a 2 over 2, and then function weight must be 4. It is because that in the previous slide, one-dimensional cases, the weight is equal to 2. However, we should perform the once again, so that this becomes the 4. Actually, this 4 is a 2 and 2. So that the result is 2. There are some big error. So that this is their error, nearly 9 point. However, 4-point rule. How can we perform the 4-point rule? W1 and W2 and specific point value equal to the minus 1 over 3 root 3 minus, and then W1 and W2. These values are always equal to 1. Similarly, they assume that value equal to the b, so that they become 1 minus b, 2 minus b, 1 minus b, in here plus b. Opposite 1 plus b, 2 minus b, 1 plus b, 2 plus b, but b is 1 over root 3, so that the calculated value is 2.182, so that they shows a nearly small error than the 1-point Gaussian quadrature. So this is a second topic of the Gaussian quadrature. So that actually that's why we learn the Gaussian quadrature in this time. It is because that we want to evaluate our stiffness matrices using the Gaussian quadrature, so that maybe our general Gaussian quadrature can be expressed looks like this. Actually we have a specific domain B transpose the elastic stiffness matrices, B, and then specific dx and dy. Yeah, so this is our general cases. However, we are going to changing the ranges so that b, in here b is a function of the x and y. However, in here b must be changing the function of the function of the s and t, and also d is a maybe constant 3 by 3 matrices. B is s and t. You should changing this one, and then this s and t maybe changing. And also, do you remember the how can we variable changing the in the two-dimensional integration? Do you remember in the one-dimensional cases? We can simply changing the some value inside in here, maybe determinant of the j, so that maybe in here we should added also same similar Jacobian. In the two-dimensional, what is the Jacobian? Maybe those kind of, do you remember? Those kind of Jacobian matrices, so that from here, so that you guys can changing maybe the from Cartesian coordination to the rotational angle coordination, we multiplied those kind of determinant of the Jacobian, so that in here we should consider the in here. Maybe tomorrow, next time, I'm going to show you the why we should use those kind of Gaussian quadrature. So that's why I already told you the isoparametric formulation. Just back into this equation again. This B matrices has a very complex shapes. Inside in here they contain the x and y. But this x and y is a position of the nodal point, so that every node point different nodal point, so that every time when you calculated or evaluated local stiffness matrices, you should calculate it every time. But just think about, we changing the domain to the well-defined domain, and then here, although their formulation slightly changing due to the variation changing, however inside in here the coordination, just think about, although I think that we should think about this Q4 element, but this Q4 element in here, the coordination 1, 1 and 1, -1, -1, -1 and -1, 1. Coordination every time same. That means that this B matrix is every time same. Also, this is some constant value, is material property. So that means that inside this integration, 3 component always same. But in here, every time we should calculate it for the every element. However, when you mapping this result here, so you don't need to recalculate it again. But every time, actually computer can do this same loop evaluation, but just think about when you're saving the specific value, matrix's value in the specific variable, you don't need to calculate it again. So this is a very beneficial for you guys. So every time we should calculate this Jacobian matrices, so that the only difference is Jacobian matrices. So actually when you solve this problem by your hand, so that you feel that what is the big difference. However, in the computational point of view, so only after the calculating the Jacobian matrices every element, you guys can easily integrate this value. Yeah, st become the plus minus 1, and so those kind of way you can easily apply the Gaussian quadrature after the multiplying the Jacobian matrices in here. So this is why we use a Gaussian quadrature. Gaussian quadrature has two benefits. First is easy numerical integration for the complex equation. Second is a mapping of the element to the specific well-defined shapes. So although I do not show the details, so however our value after the transform the B matrices and D matrices, and after obtain the Jacobian, so and then you guys can obtain that H is maybe thickness in the G direction, so that weight factor is equal to 1, so that position is you guys can easily apply it to here, so that maybe K matrices is obtained by 8 by 8 matrix. Please be sure that this matrix is a very 8 by 3, maybe 3 by 8 and 3 by 3, so the total 8 by 8 matrices, and then this is a scalar value, so the total is 8 by 8 matrix summation. So this is a good example our Gaussian quadrature system. So maybe today lectures, this is the end of the today the lecture. In the next lecture I'm going to introduce the isoparametric formulation. Iso is the same parameter, same in the integration region, so that's why you should use the isoparametric simulation. So 저희 오늘 배운 것들은요, 이제 가우시안 쿼드레처라고 해서 가우시안 인테그레이션을 많이 배웁니다. 그래서 저희가 로컬 스티프니스 매트릭스를 어쩔 수 없이 적분을 수행을 해야 될 때가 오고요. 보통 저희가 배웠던 트러스 엘레멘트나 빔 혹은 이제 삼각형 CST 엘레멘트 같은 경우에는 뭐 이렇게 가우시안 인테그레이션, 뉴메리컬 인테그레이션을 하지 않더라도 그냥 뭐 두께가 일정하다, 뭐 크로스 섹션이 일정하다 라는 식으로 해가지고 했기 때문에 그런 인테그레이션 수행을 하지 않았어도 됐었습니다. 사실 안에 있는 값들도 다 컨스턴트한 밸류였기 때문에 상관없었는데, 문제는 이제 꼭 그렇지만은 않습니다. 그러다 보니까 저희가 인테그레이션을 수행을 뉴메리컬하게 해줘야 되는데, 그 중에서도 유한요소 소프트웨어들은 모든 프로그램이 거의 가우시안 쿼드레처를 사용을 하고 있습니다. 그래가지고 가우시안 쿼드레처를 수행을 하게 되고요. 그렇다면은 가우시안 쿼드레처가 수행이 되기 때문에 사실 아날리티컬 솔루션에 비해서 에러가 존재할 수 있다라는 걸 생각을 해주셔야겠죠. 근데 저희가 이제 스티프니스 매트릭스를 이렇게 수치 적분을 수행을 하고 얻었는데, 그래서 아마 컴솔에 보시면 이제 예제를 따라 하시다 보면 제가 아마 스트레스 밸류 같은 것들을, 혹은 뭐 스트레인, 또 뭐 있죠? 디스플레이스먼트 이런 밸류들을 갖다가 플러스를 했었을 겁니다. 컴솔에서도 이런 플러스를 할 때 디스플레이스는 모르겠는데 스트레스랑 스트레인 같은 경우는 어떻게 되죠? 이 로컬 스티프니스 매트릭스에다 뭔가 영수 모듈러스라는 걸 곱하거나 이런 식으로 해서 나왔기 때문에, 거기 이제 찾아보시면은 변수를 플랫하는 후처리 부분에 찾아보시면은 스트레스 가로치고 가우스라는 말이 있습니다. 바로 이 가우스 포인트 인테그레이션 된 위치에서의 스트레스 값을 플러스를 하겠다라는 뜻이 되겠는데요. 뭐 이런 것들에 대해서 조금 살짝 있긴 한데, 저희 볼까요? 아까 인테그레이션 수행을 했는데 이렇게 가우스 마이너스 1과 1에서 수행을 했는데, 여기서 값으로 갖다가 인테그레이션 수행을 하게 되면은 값이 똑같다 라고 했는데, 저희 인테그레이션 수행을 어디서 했죠? 바로 이 싱글 포인트에서만 수행을 했죠. 그렇기 때문에 이 위치에서만 이 인테그레이션 값이 맞습니다. 다른 위치에서는 그 인테그레이션 값을 얘기를 할 수가 없죠. 이제 저희 인테그레이션을 수행을 했습니다. 그래서 그 구간의 값을 알았다고 착각을 할 수도 있는데, 우리는 특정하게 x는 0이라는 위치에서 인테그레이션 값을 취한 거다 라고 보셔도 되고요. 그러다 보니까 뭐 사실 좀 어려운 개념이긴 한데, 저희가 원디멘셔널하게 구한 다음에 뭐 변이장 같은 거 이제 변이값 나오잖아요. 그래가지고 변이값 나오고 나오고 했었을 때, 그때 안에 스트레스 이렇게 혹은 스트레인 이렇게 플러스를 했었는데, 그 값이 맞는 위치가 바로 이 센터 포인트 0번의 위치, 센터 포인트 위치에서만 이 스트레인이 맞고요. 나머지 구간에서 만약에 값을 알겠다 라고 하시면 사실은 엄밀하게 다 틀린 값이죠. 그렇기 때문에 여기에서 중심에서만 맞는 값이다 라고 생각을 하셔야 되겠고요. 만약 이걸 2디멘셔널에서도 확장해서 보신다고 하면은 마이너스 1과 1이었는데 1 오버 루트 3는 사실 여기 안에 있죠. 그렇기 때문에 이 안에서 스트레스나 혹은 스트레인 값이 정확하게 일치하는 거지, 엄밀하게는 다른 위치에서는 그런 스트레스나 그런 스트레인 값을 갖지 않습니다. 물론 이제 그래서 뭐 그런 것 때문에 뭐 얘네들을 인터폴레이션 하는 경우도 있고요. 여기서 구해진 값을 저희가 그냥 노드 값에서 구해진 거랑 뭐 똑같은 거 아니냐라고 수행을 하실 수도 있긴 한데요. 예, 엄밀하게는 인테그레이션이 수행되는 애들은 가우시안 포인트에서 정확한 값을 갖고요. 그렇지 않은 애들은 노드 포인트에서 정확한 값을 갖는다 라는 것들도 조금 그냥 한번 살짝만 기억을 해주셨으면 좋겠습니다. 뭐 어쨌거나 뭐 그렇게 중요한 내용은 아니고, 어차피 이런 상용 프로그램 같은 경우에는 이런 것들을 그냥 후처리를 너무 자동으로 해주고 있어서 많은 분들이 모르고서 쓰고 있더라고요. 근데 이제 코드를 짜실 때는 쉽지 않은 이런 걸 어떻게 처리할지에 대한 이슈가 되게 상당한 부분이 있는데, 뭐 그런 것들을 고려하지 않고 하고 있다까지만 기억을 해주셨으면 좋겠습니다. 뭐 10주차 강의는 먼저 여기까지 마치도록 하겠고요. 다음 11주차에서는 아이소파라메트릭 포뮬레이션에 대해서 좀 더 자세하게 나가도록 하겠습니다. 수고하셨습니다.